Hi, I'm James, and I'm going to take you on a journey and see how our 2002 robot actually works.
One of the requirements for this project is to create a robot that is able to path plan in a dynamic world. Not only that though, the robot must also start here and end wherever it started, while navigating through waypoints, mapping its environment, and using obstacle detection and avoidance. So if you follow me to the robotics lab, well, it seems we have a kind of an issue here where it was blocked. So the robot should be able to scan here and then find the actual trajectory to get to the final place. So hang on one sec. I wonder what's in here. This robotics lab looks oddly familiar. All right, well, time to go back to the start. Well, that was a lot easier than the last time. Now I'm all back at my start, and I completed my objective.
At the beginning of our code, the robot scans from -90 to 90 degrees. Using that scan, it is able to build a trajectory and plan a path to the nearest waypoint. The robot will scan to make sure that it is not drifting off of the path. If the original path is still valid, the robot will continue to drive along the path. However, if the path is no longer correct and is off course, the robot will need to plan the path once again. If the robot is at the waypoint and the waypoint was not the last one, the robot will find the next waypoint and then continue the process again. If the robot is at the last waypoint, it will end.
Okay, so I'm going to talk about mapping and scanning on the real robot. So the way it works is we have a robot with a given orientation in the global coordinate frame. We know its x and y coordinate, and we know its angle phi. So what we do is we scan, we get a piece of data back that says the distance to the wall and the angle that it scanned at, and that's going to be theta and d. And so given that we have these equations, we can use to calculate the position of the x and y coordinate of that blocked point. And in the framework for the software that we have a function that allows us to say, given this x and y coordinate in centimeters, what position in the grid is this? And what grid square is this? And so that allows us in the global map to block it and say that this is going to be a obstacle that we have to avoid. And then, given that we can see this, we say, oh, this must all be free space in the middle. So what we do is we take a line from the robot to this, and we do this all with integer map and grid squares. And the way it's done is an algorithm called Bresenham's algorithm. And the way his algorithm works is it takes a point and a point, draws a line between them, and gets all the grid squares on that line in between it. So this is our line right here. It goes like that. It doesn't get all of them, but it gets a very, very large subset of them. The cases where it misses lines are where there's a very small overlap of a line in a certain grid square. But given the accuracy of our scan being only a couple of degrees, it should hit all the grid squares that are free. We use the algorithm wavefront. I'm going to write that on the board so you don't forget it. And that's how we build our path. So we have a grid that we built using our line mapping and scanning and stuff. And so what we do is we say, what's our goal point? And let's say it's right here in the center of the map. This little shaded in dot right here. So around that, we're going to say the next grid square is one distance away. One here for all the nodes that surround that goal square. What it does is it says, I'm going to take this one square here, and I'm going to get all the nodes around it, and we're going to add one distance to that. And then we're going to take all of those, and we're going to do the exact same thing. So we're going to look at all the ones around that. And this is an ideal world, so there's no obstacles in this. And then we do it again for 3, and you keep building outward and outward and outward and outward until you reach some point over here, which is the robot. Now we have this nice map of the world, and we have to make a path. So what you do is you start at the goal, and you say, well, for any of these grid squares around it, this is going to be the next node to go to. So we're going to store that in the node. So this grid square right here is now going to have information about this node, saying this is the next one in the path. There are a lot of paths to get to the goal. Our algorithm will build a whole array of next nodes and stuff, and there will always be a path to the goal from the robot. And that's how we find the path. We look at the goal, we look back and say, what's the next node, 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 until you get to the robot, put those on a list, and then you have your path.
Now we're going to talk about our trajectory computation. Now one goal for our project, and especially for our software team, we want to make everything separately packaged and easily used on any robot. One reason why we felt like this goal was extremely important, because in the future, if we want to use our well-created code, then we might as well make it easy to extract. So this is a very interesting way that we decided to do our trajectory. We used a factory class to build drive functions such as drive rotate, drive arc, and drive straight. We build a queue of these I directions and then send it off to the robot to be executed. So what we do is we take that path planning algorithm that James had just previously talked about, and we take the first node, the last node, and build an ideal trajectory with the orientation we need to be in and the distance we need to go. And when the time comes that the robot's actually going to execute this trajectory, it takes into account its distance offset from the course and its theta offset. Then we're able to build a perfect trajectory and not have to worry about recomputation while the robot's actually executing.
A few parts of this worked on the real robot, and sadly some others didn't.
Due to limitations on the microprocessor and the netbook. So we found that number 2 here, if stuck in the C space, we were able to get out of the C space by going in reverse, scanning, staying on our path, and then recomputing to our trajectory. Now the interesting thing about the queue is that it allows us for a quick build and just one simple instruction. However, one thing that we were unable to accomplish on the real robot was the autocorrect trajectory. Now, this trajectory was an extremely interesting proposition because we were able to take only 2 or 3 constants in this distance formula here and find the offset that we needed for the robot to go, an arc to get to its final waypoint, and be able to compute it virtually every time. However, on the real robot, we found that when using our autocorrect trajectory and sending a second command to the microprocessor, it seemed the timers on the Java machine were unable to send an output quick enough to both motors, and therefore one motor would stall while the other kept going, causing the robot to rotate. The next thing we want to talk about is our use of the particle filter. Now we found, again, with the netbook processing, we're only able to run about 15 particles. However, the data buffer from the microprocessor to the netbook tended to back up when we overused the processor at about 75% CPU usage. Now, however, it did work, and we were able to localize ourselves. However, it was not worth using with the odometry errors that we were receiving from the actual robot while using this much processing power. But let me go into it for a little bit. So we found that we used 25 location polar particles along with 10 random particles to make sure that a robot was not kidnapped. The objects are indexed and used to compute and compare the particle data to the scanning data. Now this is an extremely crucial feature because we were able to use this not only just for detecting walls, but it technically can receive a queue of objects. Now when I say object, I don't just mean a block node as we do in Wavefront. Objects are indexed and used to compute and compare sensor data. Now this is a crucial feature because we would be able to detect cylinders, corners, and different types of objects that we actually know in real life and are able to put the sensor data and match it to an object. Now this provides a very efficient and stable particle filter, not allowing for as much processing power in the future. Another interesting fact is that we use the Box-Mueller equations to create a 2-dimensional or Gaussian wave over the actual robot location. So this way we can find if the robot shifts to the right or left, we would know a lot faster than using more random particles. And finally, can be packaged and is independent of all code. It only allows for a constructor to make it actually attached to our 3002 robot. However, this could be used in any application. As you can see in the top left, there's a particle filter screen that shows the location of all of the particles and where the robot thinks it is. On the bottom left, we find our local occupancy grid. Now, if you notice, the rays coming off of the robot show the free space from the robot to the obstacles. The blue indicates the obstacles, and then the robot is always stationary. And finally, we have our global occupancy grid. Our global occupancy grid contains green for the waypoints, magenta for the path, blue for any obstacles, and as you can notice on some of the GUI shots that we presented today, you saw red dots. And the red dots show where the particles have been in the past and where they are updating to. And finally, the pink represents the C-space around the obstacles.
You must be wondering, did our robot fulfill every single requirement? Well, it was able to operate fully autonomously within the experimental environment. It was able to effectively avoid obstacles and walls within the environment. It generated not only a local but also a global map of its workspace. It was capable of planning an admissible trajectory to move within the workspace that it created. And it was also capable of estimating its position and orientation in world coordinates. There were 5 waypoints that the robot was able to navigate to, and it made its way back after completing all 5 waypoints.
Thank you for watching our final Robotics 3002 presentation.
Sponsored in part by viewers like you.
Stay classy, RBE.